Hi, my name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to go back to galaxies again and also dwarf galaxies. I've done quite a few videos on galaxies and dwarf galaxies, and this time round I want to do one of the rarer types of dwarf galaxy actually, which are known as ultra faint dwarf galaxies. And these are kind of like a specific class of dwarf galaxy. Now before we do that, I want to recap galaxies in general and dwarf galaxies before moving on to the actual ultra faint dwarf galaxies. And if you know all of that, you've seen my last few videos, then just skip kind of towards the back end to see the ultra faint dwarf galaxies. So back to the classification system of galaxies, and it looks a bit like a tuning fork, and it has multiple branches on the right hand side for your spiral galaxies. The top branch is typically for normal spirals. They have a bulge in the center and not a bar, and the bottom branch is a barred spiral, a bit like the Milky Way. And they typically evolve the same way, so they evolve from the right hand side to the left hand side, so they move across, and the spiral arms themselves get more tightly wound. Their gas gets depleted as it turns into stars, so you find that the younger ones on the right hand side have greater rates of star formation than the older ones. The older ones get redder, the younger ones are bluer. But you do sometimes actually have a third branch there, which are intermediate spirals, and that means that they are not quite a barred spiral galaxy and not quite a normal spiral, and they have a weak bar instead. So they're kind of like a transition between the two. So sometimes you might see that as well. Now, generally, spiral galaxies, this is a massive generalization, but spiral galaxies typically have gas in them. Depends on their age, their evolutionary phase. Some will have more younger ones than the older ones because it gets turned into stars, essentially. They'll have younger blue stars. Again, the younger the galaxy, the more likely is they're going to have more blue stars, so they'll appear bluer. And they have disk-like dynamics. So they're rotating and have a net rotation and a disk-like motion essentially, and they also have spiral arms. They have large scale structure to them, which I haven't noted here, but obviously is quite an important feature of them, which is a fairly obvious one, hence the name spiral galaxies. Now, onto the ellipticals, which sit on the left hand side of this galaxy classification system, and these are mostly identified by shape, and they go from E0, which is basically a spherical shape, all the way to about E7, which is kind of cigar shaped. But it's most likely that those very elongated ones are not true elliptical galaxies. They're most likely edge on lenticulars, which it's not the scope for this particular video, but they're like a transition between the spirals and ellipticals. They share properties between the two, essentially. Now, with elliptical galaxies, they typically don't have gas, so you don't have any recent or new star formation. That means that they have older populations of stars. Their stars have aged, you don't have any new ones being formed, and they just don't have the gas to form them, essentially. They also don't have any large scale structure like spiral arms, bars, that sort of thing. They're quite smooth in appearance. And their motions of their stars is not disk-like spiral galaxies. Instead, the motions of the stars are more random. They have velocity dispersion between the stars instead, which is very different. However, quite a few elliptical galaxies do have some net rotation, but that net rotation is significantly less than what you would get in an equivalent spiral galaxy. So, dwarf galaxies then. And if we have an example of the Milky Way here, that might have a diameter of about 100,000 light years. And I'll say it might have. We're inside it. It's pretty hard to measure. But our measurements of other galaxies we can see. You're going to look on the order of 100,000 light years or so. Dwarf galaxies are going to be like 10% less than that. So not 10% less. They're going to be about 10% of that. So they could be from a few thousand light years to like 10,000 light years. So this could be quite small in comparison to like a normal spiral galaxy. And mass-wise, a dwarf galaxy is going to have a mass on the order of billions of solar masses, so a billion times the mass of the sun, whereas the Milky Way and other galaxies like that might be into the trillions of solar masses, a trillion times the mass of the sun. However, if we then go to elliptical galaxies, These are where you get your really massive galaxies, but they also have a very large range. So you can get quite small ones and quite large ones. So their range is quite broad in comparison to the spirals. But the biggest of these can actually get up to millions of light years across and tens of trillions of solar masses, or mass times the sun, essentially. So these are significantly larger, or can be significantly larger than your spiral galaxies. So onto dwarf galaxies then. These are the kind of most common type of galaxy. They're small. It does make them hard to find though, because they have quite low luminosities. They're quite small, so they're going to be difficult to find, but they're thought to be the most common type of galaxy in the universe. I suppose in the same way that we think moons might be with planets. Like most planets have got more than one moon. So if we were to sum up all of the moons in the solar system and all the planets, we have more moons. Same thing likely going off here. So where are they found? Well, quite often we find them orbiting around the outside of larger galaxies. So the Milky Way has lots and lots of satellite galaxies or dwarf galaxies that are orbiting it. Over time, they do kind of merge with this Milky Way, they interact. So these smaller ones can get tidally distorted, pulled apart, and end up becoming part of the Milky Way. And this is quite common for other galaxies as well. So we typically find them around the outside of other larger galaxies. That's not always the case. Again, bit of a generalization, but we quite often find them there. So common types of dwarf galaxy. You've got dwarf ellipticals, you've got spherical ones that are like spiral galaxies and irregular, and all of those share quite common properties with their larger cousins or siblings, I suppose. They have similar sorts of shapes, similar sorts of compositions, but that's not always the case. There are subtle differences, hence the names are just dwarf elliptical, dwarf spiral, because they're kind of smaller versions of the big ones. Now there are some uncommon types, which are kind of likely to be subtypes of the common types. They could be. You've got ultra compact, ultra faint, and blue compact. Now the focus of this video is going to be ultra faint. I've done other ones on ultra compact, blue compact, and the common types. So this one is your ultra faint dwarf galaxy. Now, what are they like? Well, just like all dwarf galaxies, they're small and very faint, but more so than other dwarf galaxies. And I suppose the clue's in the name again. They're ultra faint. So these are actually fainter than a fairly typical dwarf galaxy. And what I've got there on the left-hand side is a ultra-faint dwarf galaxy, and you can barely see it with respect to the actual the foreground stars, essentially. And they do look a bit like a star cluster. They're just not very bright, essentially. So that's why they're very, very faint. Now, globular clusters, which look quite similar, are like spherical groups of stars. They don't have any gas in them or anything, and these orbit around the outside of galaxies. So the Milky Way has loads of these globular clusters. They're quite old objects, essentially. They're quite old stars. I mean, if you look carefully, there's actually blue stars there, but ignore that for now. So these are quite densely packed clusters of stars, and ultra-faint dwarf galaxies kind of resemble them. So they can look quite similar, but they're not globular clusters. It should be pointed out that they are distinctly different, and there are some properties of them that are different from a globular cluster, despite potentially looking quite similar. They do contain like hundreds to thousands of stars, so not that dissimilar to maybe globular clusters. Globular clusters can have, significant amount of stars as well, but the interesting thing here is that if we compare these ultra-faint dwarf galaxies to globular clusters that are similar sized, they will have significantly lower luminosities, or magnitudes. It is here, absolute magnitude. So they're basically fainter. Again, clues in the name. Now this is a plot here that shows these ultra faint dwarf galaxies, or dwarf galaxies in general, which is on the right hand side, which are like the blue circles, different sorts of ones. These are ones that have been confirmed dwarfs, suspected and unclassified ones. And then you've got the other ones on the left hand side, your globular clusters, which are not coloured. and you can see that actually they're much larger in comparison to their absolute magnitude. So for an equivalent size, they are much, much fainter. And that basically means that they're more extended. So these ultra faint dwarf galaxies, they have a larger extent to them than a globular cluster. So they're going to be larger in size, but not necessarily have an overall brightness anymore. So the stars are likely going to be more spread out, not going to be as densely packed. And you can see the difference here between a globular cluster on the right-hand side and a ultra-faint dwarf galaxy on the left-hand side there. So more extended, a bit more diffuse, I suppose, than a globular cluster. Now, the really interesting thing about these galaxies is these are the most dark matter dominated objects known. So these have the most dark matter per size, unit area. Well, I don't really know what the best way to say this is, but they are dominated by dark matter. And that's actually really good for astronomers because we can use those as like studies for dark matter. So very unusual, and this is what stands out different from globular clusters. Globular clusters don't have this, whereas ultra-faint dwarf galaxies do. So that's a big significant difference. Now, this is where it gets interesting for our studies at least. These are the dwarf galaxies of the Milky Way, and this is the number that we knew as a function of time. And basically, as we start doing our surveys, our telescopes get better, we find more and more. And at the moment, we've got kind of pretty close to 60 dwarf galaxies or satellite galaxies orbiting around the outside now. And we can see those relatively easy. I think that's got to be careful there because they're quite faint, but they are close to us. They're not another galaxy a long way off. They're relatively close. And because of their significant amount of dark matter, it makes them great for studying dark. Yeah, basically, they're good laboratories for studying dark matter. So if these are orbiting around the Milky Way, these are known to have the large or be dominated by dark matter in comparison to other objects. They have these dark matter halos. We can study those because they're going to be our closest dark matter halos on small scales as well. So they're fantastic laboratories for studying dark matter, which is what's going to happen kind of in the future, because we've only really started to find these with our new equipment. These are not things that we really knew about, a long time ago. We're starting to find lots of these. So these are going to be fantastic laboratories for learning more about dark matter in the future. And how do they actually form? Because again, they're a little bit unusual. Well, one of the potential routes for formation could be dark matter mini halos. So you have these kind of like mini dark matter halos, and then the gas kind of collapses inside there. You get the stars forming once it's cooled down enough, and that could be one of the routes. So actually, there's a few different ways, and these could be primordial galaxies as well. These could be some of the first galaxies that formed in these dark matter halos. So studying them is going to help us understand a little bit more about the early universe. So if they are the first galaxies, then if we can study these in great detail, we might be able to understand how the first galaxies formed, what the early universe was actually like more. So they are going to be very good objects to study going forward. So thank you for watching, and if you enjoy or you find the videos helpful, then do consider becoming a member of the channel. There's extra videos in the member section. It also helps support the channel in general, and there's also other benefits as well. So thank you for watching.